Okay, here go my video reassessment for standard number 3. So homework problem, one of the assigned homework problems from chapter 38, quantization. Just chose the homework problem that looked similar to me, like a question that was on a standard. Uh, so here it goes. Okay, homework question number 6. A photoelectric effect experiment finds a stopping potential of 1.56 volts when light of 200 nanometers is used to illuminate the cathode. Part A, from what metal is the cathode made? And part B, what is the stopping potential if the intensity is doubled? Okay, basically just writing it as if I was teaching it to someone. So basically I just kind of take it step by step, and I start out by saying, all right, so first off, to tell what metal the cathode is made of, I need to know the work function of the cathode, which is basically just E naught. And then from there, I could just view the table of the different the different work functions for the different metals. Right. So basically, all I need to figure out is the work function of this specific metal, and then I'll be able to find out the metal. So basically, in able to find out the work function, I just thought of equations that I know related the work function, and one is the equation for the stopping potential. So therefore, for the stopping potential of we know that it's the maximum kinetic energy divided by E. Okay, which we then know is the maximum kinetic energy basically is the energy of the electron minus the work function. Because basically this is the energy that the electron has before it is emitted from the cathode. So basically, therefore, if you subtract the energy needed, the minimum amount of energy needed in order to get that electron to emit, that'll be the maximum kinetic energy. And if we just divide that by E, we get our stopping potential. Right. So therefore, I said in order I could use this with some algebra in order to figure out E naught. So this is what I got. I got E naught is equal to HF minus the stopping potential times E. And basically, I know that H, I want to relate that in terms of electron volts, Planck's constant in terms of electron volts, since I know that the work function that I want needs to be in terms of electron volts. So therefore, H in terms of electron volts is 4.14 times 10 to the negative 15 electron volts per second. The frequency, which I calculated here, I know the wavelength of the light is 200 nanometers. Therefore, I know that wavelength is equal to the speed of light divided by frequency. I can use that to find the frequency since I know the wavelength. I got C over lambda is equal to frequency, which is C, as I know, is 3 times 10 to the 8. And lambda is 200 nanometers, which is 2 times 10 to the negative 7 meters. Therefore, I get a frequency of 1.5 times 10 to the 15 hertz. Okay, all clear and dandy. But somewhere in this problem, something just isn't working out right. I don't know where. I've been going. It's a simple problem, so it's very frustrating that something isn't adding up right. But whatever it is, I've been looking over it. I've been trying to work it out different ways, and it's just not adding up right. But I thought that I put this much effort into this problem, I should submit it and then just submit it as my video reassessment. And I don't know, hopefully you can help me figure it out, or hopefully it'll make sense in the morning. But then, so basically just plugging and chugging. I mean, H, Planck's constant, is 4.14 times 10 to the negative 15. The frequency, which I calculated here, is 1.5 times 10 to the 15 hertz. Yeah, this I don't know why I wrote this twice. It's kind of late. V stop was what they gave me, which is 1.56, and then E, which is the charge of an electron, is 1.6 times 10 to the negative 19 coulombs. And for some reason, I keep getting 6.21 electron volts when I know that just isn't right, because on the table there's no element with um, a work function of 6.21 electron volts. So something isn't adding up, but I'm gonna figure it out, resubmit it, and then yeah. And then part B asks, what is the stopping potential if the intensity is double? Well, we know just from intuition that the stopping potential does not depend on the intensity of the light. If you increase the stopping potential, that doesn't mess with. I mean, yeah, if you increase the intensity of the light, that doesn't bother the stopping potential. Both weak and intense light will have the same stopping potential. And yeah, that's it.